So we just finished talking about phases of matter, and now we're going to move on to talking about temperature. So temperature is going to be a measure of the internal energy of an object. So remember we talked about kinetic and potential energy before, which was motion or stored potential. In this case, we're talking about the energy within a substance. So within water, within the metal pot, within a piece of wood. So the internal energy inside. Now, we measure an object's internal energy with what's called a thermometer. You guys are all familiar with thermometers. Different kinds, I'm sure. The kind that go into your tongue, the kind that read your forehead, the kind that go in your ear. There's all kinds of thermometers, and the kind that you use in a lab. So thermometers are used to measure temperature, which means they're kind of measuring the internal energy of the object. And they rely on thermometric properties, which are specific to different types of substances. We know that glass is going to behave differently when exposed to heat than metal, as is wood and as is plastic and styrofoam. So they all have unique or semi-unique properties. And a lot of that has to do with their ability to conduct electricity, which we'll talk about in a few chapters. So some examples are bimetallic strips and thermostats. So this is an example of a fire alarm. And if you look on the right-hand side, there is a coil of wire. Now, when that coil of wire begins to heat up, it's going to expand. And when it expands enough, when there's a fire or a large amount of heat, it's going to eventually touch a sensor, which is going to set off the fire alarm. So that's how your fire alarms in your house work if they're older. They are a little bit different now because not all fires produce a large amount of heat. Some of them produce smoke, which does not have the same heat that a fire will. And so some of the fire detectors now, which are smoke detectors too, are a little bit more sophisticated than this image. And so what it looks like, if you want to see a cartoon schematic, is you have this bimetallic strip, which is iron and brass. When the strip gets heated up, so you see the Bunsen burner here, it's going to bend because brass is going to have the higher expansion rate, meaning it's going to expand faster, which bends the iron, and then it will hit a sensor, which then sets off a smoke detector, fire alarm, or sprinkler system, whatever you may have there in your facility. So temperature scales, they are going to be defined. WRT means with respect to various reference points. Okay, so we're picking important reference points and we're defining our scales with respect to them. Now, these reference points happen to be the two common points of a very common substance, which is the boiling point and the freezing point of water. Water is like 78% of our world, and if we can define the freezing point and the boiling point that's commonly attained, then we have a good reference to base off of. We're going to see that in chemistry that water is an important substance. It's going to be kind of the baseline data we saw with density. Density of everything was measured in relation to water, which had a density of 1. So we're going to see this recurring thing about the importance of water. So our three temperature scales are Fahrenheit, Celsius, and Kelvin. Okay. So if we're looking at the image, we have Fahrenheit, Celsius, and Kelvin in that order. And you can see that the top point is the boiling point of water. So in Fahrenheit, it boils at 212. Celsius, it's 100. Kelvin, it's 373. So the important thing I want to point out here is that it's degrees Fahrenheit, degrees Celsius, and it's not a typo. It's not correct to say 373 degree kelvins. It's just 373 Kelvin. It's named after Lord Kelvin, who was a scientist. There are no degrees with kelvins, so it's incorrect to do that. Now on the bottom side, we have the freezing point of water, which is 32 degrees Fahrenheit. That's a value that we're more familiar with because we know that if it's raining outside and the weather person says it's 32 degrees outside, the first thing you're going to think of is ice on the road. 0 degrees Celsius is the freezing point, and 273 Kelvin is the freezing point. So the important reference points here are that the Celsius scale runs from 0 to 100. Okay, just like a grading scale, 0 to 100, freezing to boiling. And then on the very, very bottom, we see absolute zero. And this is where Kelvin comes from. So Kelvin measures at 0 degree Kelvin, or 0 Kelvin. There is no such thing as negative Kelvin. So at absolute zero, in theory, all molecular motion would stop. We don't know that that's actually what will happen because we've never been able to recreate 0 Kelvin, but that's its reference point is that at 0 Kelvin, all molecular motion would stop. And so 0 to 373, and it can continue to get hotter, is the typical scale for Kelvin. Okay. Now, in our practice assignment, we're going to talk about Fahrenheit to Celsius, Celsius to Fahrenheit, and Celsius to Kelvin. You're also going to do a lab that's about determining the formulas to convert between the two. So we're not going to write the formulas out now. We will get to them when we practice. So what is heat? So normally I start this lecture and say heat and temperature are not the same. You probably think they're the same, but by the end of this, I hope you know that they're not. So what makes them different? Well, temperature was the measure of an internal energy. We measure it with a thermometer. Heat, on the other hand, is when energy is transferred between objects. So heat is like an action. Temperature is not an action. Temperature is a measure. So a measure of the energy that has been absorbed or transferred is how we determine heat. So, but we don't have heat unless there's a transfer. So you can have two objects. You can have a hot cup of coffee and a cool spoon, and they're going to have their own temperatures. But until you put the spoon inside the coffee and start to stir, and the spoon starts to absorb the heat from the coffee, that's heat. When you keep them separate, they have temperatures. You put them together, and the coffee cools down and the spoon heats up, that is going to be heat. So there are two related processes, heating and cooling. So if you think about what I just said, the spoon heats up, the coffee cools down. Because if heat is lost by one object, it's got to be gained by something else. Because heat is conserved. Because it's energy. And energy is conserved. Remember we talked about that in chapter 3. So there are two different types of heating methods. One is temperature difference. So taking something hotter and something cooler, putting them together. And what we're going to see is that the energy is always going to go from the higher, hotter region to the cooler, lower region. So we don't technically cool hot objects. We are normally heating up a colder object, and because the hot object is losing its heat, it's going to cool down. But it doesn't flow the opposite direction. The second heating method is energy form conversion. And so this is the transfer of heat by doing work. A really great example, obviously, is this person pushing a table. But an even more relatable example is when your hands are cold and you're outside, you're going to rub your hands together. And we know that if you rub your hands together, they will eventually get warm, right? And that's because you're doing work. You're creating a force between your hands, friction force between your hands, which then becomes heat. And so that's an example of energy form conversion. Okay, if you rub something like your feet on carpet and you scoot your feet along and you make really good contact, you're going to heat your feet up for that very same reason. Okay, temperature difference would be holding a cup of warm coffee to warm your hands. You're not doing any work. The only thing that's happening is the hot cup of coffee is warming your hands because your hands are cooler. So two examples of how heating methods are different. So how can we think about heat versus temperature? If temperature is a measure of hotness or coldness, we measure that with a thermometer. We use a number and a unit to express it, 25 degrees Celsius versus 100 degrees Celsius. While heat is going to be a measure of the amount of heat produced. Warmth or coldness. So doubling the amount of something at the same temperature will double the heat. So for example, if you have 1 liter of water versus a fourth of that, 250 milliliters of water, and they're both at the same temperature, and you need to cool down the water to a certain temperature. So say you just brewed hot tea, and you have a huge gallon and a small cup of hot tea. You probably know from life that it's going to take a lot more ice to cool off the gallon of tea that you just brewed versus your small cup. That's because there's 4 times as much in the gallon as your cup. So it's going to take 4 times as much ice as the small cup. Another way to think about it is the difference between the image in the middle and on the right. Say you are outside at a bonfire and it is really cold and you are trying to stay warm. Are you going to want to huddle around the one single match, or are you going to want to huddle around the bonfire, the large one? Well, you probably say, of course, I'm going to want to be around the bonfire. And why? Because it's producing more heat. But why? Because there's more wood. And as we have more wood versus the match, we're going to have more heat. So heat is what we call mass dependent. It depends on how much matter we have. If I have a lot of something, it's going to produce a lot more heat, or it's going to take a lot more to cool it down than if I have a little bit of something. Okay? But temperature is not mass dependent. If I boil water, it doesn't matter if it's a pot of water or a cup of water. It's going to boil at 100 degrees Celsius. Both the match and the bonfire are burning at the same temperature. They are just not producing the same amount of heat. So that's the best way I can explain it. And I hope that either one of these is a relatable example to your life, because you need to be able to keep heat and temperature distinct in your mind. So specific heat is a variable. It's how we determine how things heat up differently. Okay, so there are going to be important variables in heating, and at the bottom you see the formula. It's Q, which stands for heat. Sometimes it's capital Q, sometimes it's lowercase q. Mass is M. C is the specific heat constant that we'll talk about, and T is the change in temperature. So the things we're going to look at for is, what kind of temperature change are we looking for? Are we going from 0 degrees Celsius to 100 degrees Celsius? Are we only going up by 10 degrees? The mass is how much, because remember, heat depends on how much. C takes into account the different types of materials, because not all materials heat up the same way. So different materials will require different amounts of heat to produce the same temperature change. So while it's probably relatively easy to heat up metal, it's not going to be necessarily as easy to heat up something like glass or styrofoam or different types of metal. So in the end, we get a measure of specific heat. And I call this the MCAT equation. So hopefully you can see why MC, the delta triangle looks like an A, T. So looking at the image, we have 10 grams of each substance, 10 grams of aluminum, 10 grams of copper, and 10 grams of gold. We can see that the size of the cubes gets smaller. That reflects the relationship between how much aluminum it would take to get 10 grams versus it doesn't take as much gold to get 10 grams. Now, we're taking all 3 substances and heating them up from 20 degrees Celsius to 100 degrees Celsius. And what we see is that it's going to take 176 calories to heat aluminum up, 74 calories to heat copper up, and 24 to heat gold up. So that's the red arrow going to the left, pointing from left to right. So we can see it's going to take a lot more heat to heat the aluminum up versus the gold. And the reason why is because they have different heat capacities. And we can see that in between the arrows there's a little C value. C for aluminum is 0.22, C for copper is 0.93, and C for gold is 0.03. So the value gets smaller, meaning it takes less heat to heat gold up than it does aluminum. So aluminum takes a lot, which is why it makes really good materials for planes and really good construction materials. Aside from the fact it's really light, you would not want to build a gold plane and think you're going to fly it, because it's going to be very heavy and it's going to get very hot once it's up in the air. So heat flow. There are going to be 3 mechanisms for heat transfer due to the temperature difference. So this is ignoring that energy work that we talked about. This is not rubbing your hands together. This is holding the cup of coffee. So the 3 different methods we're going to talk about are conduction, convection, and radiation. And remember that the natural flow is always from higher to cooler. So we're not changing that rule. So conduction is going to be heat flowing through matter, and the way it works is that hot atoms are going to start bouncing around like jumping jelly beans, and they're going to collide with cooler atoms. And when they collide with the cooler ones, they're going to transfer some of their energy. It's like tag, hear it, or like the wave. The direct physical contact is required, so they can't transfer heat unless they collide with each other. Therefore, it cannot occur in a vacuum, meaning it doesn't happen in outer space. Now, the rule is that something must be a good conductor. These are things like metals. Poor conductors are going to be insulators, so they're not going to conduct heat well. So styrofoam, air, wool, glass. And so if you look at this image here, we're heating up the metal pipe on one side, and there's little thermometers. And you can see that the thermometer that's the closest to the flame has the highest red line, meaning it's the warmest. And as you get further away from the flame, the temperature goes down. But if you were to heat up enough, eventually all of the thermometers might continue to rise. But this illustrates the little atoms colliding with each other as they travel down the metal pipe. It's why if you hold a coat hanger into a fire with the marshmallow, it takes it a little bit before your end of the coat hanger gets warm, but if you go to grab the marshmallow right off of it after you've heated it up, that end is going to be very hot because those atoms are colliding a lot more and it hasn't quite traveled down the length of the coat hanger. Convection is going to be energy transfer through bulk motion of hot material. The two places this happens is in water and in air. So convection does not happen in solid materials. Water, liquid, gas. Some examples are a space heater or a gas furnace. So what we see is that warm air, so if we have a heater, the air is going to warm, it's going to rise because warm air rises, it's going to cool off, sink back down low as cool air. And so that circular motion that we see is the convection. And it's always going to be that hot air rises. This is going to help us produce, when we get to earth science, when we talk about winds, we're going to see that convection has a lot to do with our global and local wind patterns. And it also has a lot to do with our underwater sea currents and the distribution of salt water in large bodies of water like ocean. Okay, so convection will come back. Radiation is based on radiant energy, which is energy associated with electromagnetic waves, and it can operate through a vacuum. So this is essentially how we receive warmth from the sun because radiation can travel through space. Everything on Earth, no matter what, is going to not only absorb radiation, but it's going to emit radiation. The thing is, we don't all absorb or emit at the same rate. So some things are going to emit radiation and then hold on to it quite well, like the ground, whereas some things are going to dissipate most of the radiation they absorb. So like the clouds, they're going to absorb radiation, but they're also going to release it quite well too. So the temperature of either the global or the local area is going to depend on the balance between the rates of emission and absorption. So as well as the relationship between the sun and the earth's patterns like seasons, and we'll talk about that. But globally, if we want to think about the relationship between how much is being absorbed and how much is being emitted, we know that this contributes to overall global warming. Currently, we are absorbing the same amount of radiation. However, we are emitting a lot more. Therefore, the overall global perceived is going to be higher. Also, what happens is when you have things like the hole in the ozone layer, which allows a lot more of the radiation to come in, it's going to be essentially a higher level of absorption and not so much emission. So when radiation comes in to the earth, it also leaves. It doesn't always stay here, but right now the balance is a little bit different. We're kind of holding on to some of our radiation because of smog and pollution and things like that that are man-made. But we know from times past in geologic history that we have periods of cool and periods of hot. It's not unknown for us to go through an ice age that's mild or a warm age that's mild. The concern is, are we going into a large swing where the temperature of the earth continues to heat up, and what does that mean if we don't come back down? So we're going to take a break. You're going to practice the temperature scales. So you'll find that assignment where you found the lecture material, and then you'll come back and we'll finish up just the last few slides of the lecture.